Hello, and I would like to welcome all of you to Writing Faster SQL Server Queries Part 1, hosted by Experts Exchange and Tim Chapman of SQLServerNation.com. I am Jen Prentice with Experts Exchange, and I would like to personally thank all of you for listening to this webinar. If you tried to log into the live webinar a few weeks ago, we do apologize. We experienced some technical difficulties, but we are pleased to be able to be sending you this recording. For those of you who are not familiar with Experts Exchange, we are a technology help website where professionals can go to get answers for their technology-related questions. If any of you would like to know more about how Experts Exchange can benefit you and your business, my contact information will be available at the end of this webinar. But enough with the sales pitch, on to Tim. Let me say that we are thrilled to have Tim as one of our top experts on Experts Exchange. When he's not helping members of the Experts Exchange community, Tim is a SQL Server consultant specializing in system architecture, administration, and performance tuning. He is also the co-owner of SQLServerNation.com, and he has passed the SQL Server 2005 and 2008 MCITP tests for database administration and database development. And last but certainly not least, in 2009, Tim was awarded the prestigious Microsoft SQL Server MVP Award. So without further ado, I give you Tim Chapman.
Well, thank you, Jennifer, for the great introduction. And I would like to express my apologies for the technical difficulties that we had last week for the webinar. I was looking very forward to doing it, but again, we'll just press on with this. We are recording today, Writing Faster SQL Server Queries. My name is Tim Chapman. We're going to use this as a demo-only session. Going to look at a lot of different ways to write SQL Server queries, how we can take one query and tweak it a little bit to squeeze a little bit of performance out of it just by using a few native SQL Server tools and taking that where clause and kind of rewriting it a little bit. And we're going to look at some really efficient ways to write SQL Server queries. We're going to look at some very inefficient ways to write SQL Server queries, and we're going to kind of compare and contrast those as we go through the demo. So let's go ahead and get started. First, we're going to look at the where clause, which is the fundamental way to set criteria with our SQL statements. Okay, all the demos that we're going to look at today are going to be against the AdventureWorks database, which is a database freely available on codeplex.com, created by Microsoft, has a lot of rich data loaded into it, and it works wonderfully for the examples that we're going to look at today. I'm going to look at the amount of I/O generated by our queries, and we're going to look at the execution plans as we go through these queries. Okay, I'm not really going to dig into the execution plans. I'm going to save that for a later webcast that I plan to do probably at the beginning of 2011. So we're just going to look at some basic iterators in our execution plans to give you a feel for kind of what's going on with these plans and how SQL Server is going out and fetching the data for these queries that we're running. So first, I'm going to set statistics I/O on. Okay, that tells SQL Server to return to us the amount of I/O that's generated by our queries. Okay, I/O is a resource-intensive operation. Okay, it has to go down to the disks to return data from disk into memory and then read it from memory to serve our query. So the less I/O that our queries generate, the better off we are. Okay. Also going to look at the execution plans. So right-click and go to Include Actual Execution Plans to look at a graphical representation of the plan for that query. Okay. First query we're going to look at, we want to return all records from sales.customer where the modified date occurs on 2/23/2007. Okay. The modified date column is a date time data type. Okay. That means there is a date aspect and there is a time aspect to this column. Whenever we are comparing it to just a date, we have to do something with those time values, okay? Unless they're all midnight, in which case we're okay. But in this case, they're not. We have some time aspect to the records in our table, so we have to strip out that time. So one way to do this is to use the convert function, okay? Take convert, pass modified date into convert. I want to return a variable character string, which just returns the date based on the 101 format that I'm passing to it. And then I'm going to cast it back as a date time, and then I'm going to compare that to 2/23/2007. Okay, it's kind of a roundabout way of just stripping out that time. It's also an inefficient way to do it. Okay, the reason for that is that because we are using this convert function, we have to perform that on every single record in this index. And that ends up being a very intensive operation just because we have to traverse every single record in the index and compare the result from that function call to 223-2007. So let's go ahead and run this query. Okay. Notice that we're going to have 24 records returned here. Okay, 24 records returned, and I have 3 tabs. I have my results tab, I have a messages tab, and I have an execution plan tab. Okay, execution plan tab has came up because we right-clicked and we chose to include the actual execution plan. Okay, here's the results. We returned 24 records. Looking at the messages column, here is the results from our set statistics IO statement that we set up here. Okay, what we're really interested in here is the amount of logical reads returned. Okay, these are the number of pages, index or data pages, that are read into the buffer cache, or the portion of memory that holds data pages, and used to service our query. In this case, there are 38 index pages read into memory to serve this query. Okay, looking at the execution plan, excuse me, we have an index scan. Okay, that index scan means that we had to basically touch every single record in this index and compare the value in that index to 223-2007. Now, I'm mentioning that we're comparing every single record in the index. In this case, we are just touching the index because we don't have to go out to the base table. The non-clustered index that we have on modified date actually contains the modified date values, okay, and a pointer back to the clustered key for the table, which I'm not going to get into today. But we are really just traversing that particular index for this query. Okay. Another way to write this query is to move that functionality away from the modified date column. So here we're performing all this functionality on the modified date, which makes us really unable to use that index in an inefficient way. Okay, we're not able to seek. We have to traverse every single page or record in that index. One way to do that is to move that functionality away from the modified date, so we're really just kind of performing a range-based seek. So here I'm setting criteria. I'm setting where the modified date is greater than or equal to 223-2007, and, so here's the conjunction, and the modified date is less than 224-2007. So everything in 223-2007 up to but not including 224-2007. Okay, run this query. Excuse me. Have the same 24 records returned as before, looking at the messages column, and now we have 2 logical reads as compared to the 38 logical reads that we had before. Again, the fewer number of logical reads or fewer number of IOs that you have to service a query, the better off you are. Okay, just by taking this functionality away from that modified date and moving it to the other side of our operand here, we get a significant performance gain. Looking at the execution plan, and now we have an index seek. So we were able to traverse to the specific spot in our index where we know our modified dates occur and just select those pages that we need. Okay, it returns a much more efficient operation just by a simple rewrite of our where clause. Okay. Take a look at another example here. What if I want to return all the records from our sales.customer table that have occurred more than 6 years in the past? Okay, compared to 12/16/2010, which is just a few days ago. One way to do this is to add 6 years to the modified date column and then compare that to 12/16/2010. Okay. A different and more efficient way to do that is to take that functionality away from the modified date column, segment the modified date by itself, and then subtract 6 years from 12/16/2010 and do the comparison that way. Okay, let's take a look at the comparison of these two queries. If you highlight both queries and you send them in the same batch with the execution plan on, you can look at the relative cost of each query. So let's run these queries. Okay, each one returns around 670 records. Okay, logically exactly the same query, just rewritten a little bit differently. Looking at the messages column, we see the IO results from both queries. Okay, for the first one, we have a logical reads of 38 as compared to 4 for the second query. Okay, the second query being us having the modified date by itself, so that we're able to actually perform an index operation on that modified date and not have to traverse every single record in that index. Okay, looking at the execution plan, as you may suspect, with the operation on the modified date column, okay, we result in an index scan. Okay, we have to scan every single record in that index. Whereas if we have the index by itself, okay, and specifying criteria on the specific date that we're looking for here, subtracting 6 years from it, we return an index seek. And the relative cost of the first operation is 91% overall. So there's a 91% overall relative cost of performing this operation as compared to a 9% overall cost compared to running this operation. So a much more efficient operation just by taking that where clause and kind of massaging it a little bit, getting the modified date off by itself so we can use an index on it to perform that lookup. Okay. Come down here. What if we want to look for all the records in the sales.customer table that were modified in 2005? Well, a very intuitive way to do this is to use the year function on the modified date column. Here we are passing the modified date to the year function and then comparing the result from that function call to 2005. Okay, a very intuitive way to do this, and a way that I've seen used numerous times over the years, but it's not an efficient way to do it. Okay, taking this query and kind of, again, massaging it a little bit so that we have a range-based seek, we can look for anything where the modified date was greater than or equal to 1/1/2005 and where the modified date is less than 1/1/2006. So anything where it's greater than or equal to 1/1/2005 and up to but not including 1/1/2006. Perform the exact same functionality, but in a little bit more efficient way. Okay, run these two queries together. Each result set returns 15 records, the same result set for each. Looking at the messages, we have 38 compared to 2, so a much more efficient operation just by performing that range-based seek here. And then looking at the execution plan, we have an index scan versus an index seek, a 94% overall cost versus a 6% overall cost, so a bigger win just by moving that functionality away from the year clause or the year function and moving it to a range-based seek as we have here. Okay. One last example for the where clause, and we're going to kind of move on. Here is a very contrived example. You wouldn't necessarily see this type of functionality, but I want to kind of stress the fact that anytime you have an indexed column that you're specifying criteria against and you're performing some sort of operation on that column before you're applying that criteria, that operation that you're applying against that column is 99 times out of 100 going to cause you to not be able to use an efficient index operation on that column. So here, just doing a scalar aggregate, counting the number of records that match up to 710, the product ID 710 in sales.sales order detail, doing the same functionality here, but here I am multiplying both sides by 2. So here I'm multiplying every single product ID by 2, multiplying the 710 that I'm looking for times 2, which results in 1420. Run that operation, and then we'll get an idea for how inefficient that is. Okay, the exact same result sets will be returned, except one's going to be a lot more efficient than the other. Okay. Run these two, 44 records returned for each query, looking at the messages. For the first operator where we're just doing a specific seek on 710, we have 2 logical reads, whereas here, whenever we're doing the multiplication for each one, we have a logical reads of 228. So a much more efficient operation just doing the specific seek of our particular product ID as compared to our contrived example where we're multiplying each side by 2 and then performing the operation that way. So again, this example doesn't necessarily make sense for a production environment, but it does kind of stress the fact that any sort of operation you do against a index column can come back to bite you in terms of performance. Okay? Let's move on to count versus exist. So Exists is a short-circuiting operator. Okay, it takes a query, and then as soon as the database engine returns at least one record meeting the criteria in that query, it returns true. Otherwise, it's going to return false. So here I am passing a simple query to the exist operator. Okay, as soon as at least one record is returned from the exist operator, it's going to print out exists equals true. Okay, if we just run this query by itself, we see that there are almost 4,700 records returned. Okay, let me go ahead and look at the actual execution plan for these. I include actual execution plan. So let's go ahead and run this, and you can see that before, whenever I ran this query by itself, it returned around 4,700 records or so. Looking at the logical I/O, we had 11 logical reads to satisfy this query. Okay, so let's run this inside the exist operator, and we'll get a feel for what's going on. So here we have 2 logical reads returned as compared to the 11 before, because whenever we ran this before, we looked for every single record where it matched product ID 870. Here we're just looking for one record that does. As soon as a record is returned that does, we return true and our query is over because it was an existence check. Okay, looking at the execution plan, we have an index seek. Okay. Another way to check for existence of a specific condition is to use the count operator, or the count aggregate, rather. It's a scalar aggregate. It always returns a value. So here, looking at the count, I am able to return that there are, again, the close to 4,700 records that we had before. Okay, looking at the messages, we have the 11 logical reads, which we have to scan every single, or we're basically seeking where the product ID equals 870, which takes around 11 logical pages to return that. Looking at the execution plan, we have an index seek with our aggregate here. Okay, again, I want to note that 11 logical reads were returned. So whenever I perform this operation, I am taking this count, I'm assigning it to a local variable, and then I'm kind of interrogating that local variable here, and then if it's greater than 0, I'm going to return true. Okay, run this query by itself. Okay, again, we have the 11 logical reads, whereas we had 2 before whenever we were using the exist because it's a short-circuiting operator. Looking at the execution plan, we still have our index seek with our aggregate, but because we have to go and return every single record that matches this criteria, it's an inefficient operation to just check for existence. Okay, so if we want to compare these 2 queries against each other, we can highlight them, run them together. Again, we have the 2 logical reads versus the 11 for the count assignment to the local variable. Looking at the execution plan, we have a 16% overall cost for the exist clause versus an 84% overall cost for the count. They both perform index seeks, but because the exist clause is a short-circuiting operator and returns true for the first sign of a record that's going to be returned for our predicate, results in a much more efficient operation. Okay. Now I want to show you another example here, just for good measure, but it's kind of one of those where you don't necessarily want to take this course of action, but I want to show it just to be thorough. So here we have the same exist clause that we were looking at before. Here I have the same count clause, but I am using the count aggregate inside an if clause. Okay, doing this, SQL Server notices that these are the same patterns, and it just started doing this within the past few versions, I believe. Notices that these are the same basic overall patterns. So here I'm checking for existence. Here I'm also checking for existence, and seeing that the optimizer knows that these are the same patterns, it's able to kind of rewrite this query for us. So if we highlight these together, and because I'm not assigning it to a local variable, I do not have to go and return all the records. SQL Server is smart enough to know that these 2 queries are essentially exactly the same. They're both checking for existence, so it's able to rewrite this in such a way, here, this count inside the if clause, so that it performs exactly the way that this exist does. Now, I only show this to be thorough. I do not recommend using this approach of putting this aggregate inside the if clause, just because you never know if this functionality is going to go away. Here you know how exists works. Here this may always, and hopefully will always, work this way, especially for old code that does this, but you can't depend on it. Okay, it may go away someday, so for good measure I always recommend using exists for existence checks instead of a count aggregation inside of an if clause. Okay? On to parameter sniffing. So this is one of my favorite demos to show just because it shows a wide range of insight into kind of what's going on inside SQL Server under the hood. So we're going to kind of take a look at what's known as the plan cache inside SQL Server, or the plan cache is a portion of memory inside SQL Server that basically holds execution plans. Okay, these execution plans stay in memory so long as they're not any pressure or they're aged out or something like that. So long as they're useful, they'll stay in the plan cache. Okay, so any sort 95% of the queries that we send to SQL Server will stay in the cache. There are some that do not stay in the plan cache, but for the most part, any query that you run will be in the plan cache with SQL Server 2008 or 2005. So here I want to create a temporary store procedure, and in this store procedure I am going to look at a couple of DMVs. I'm going to look at sys.dm_exec_cache_plans. This DMV returns the plans that are in our procedure cache. Okay, it's a new DMV included in SQL Server 2005. Here I'm using the cross-apply operator, also new to 2005, and I am passing the plan handle from exec cache plans to return the plan for that particular query. Okay, so I'm going to go and run this to create my temporary store procedure. Okay, here I want to basically clear out any plans that we currently have in memory. To do this, I use dbcc free proc cache. I don't recommend this on a production environment just because most of your applications are going to depend on plans that you already have in cache, and so if you clear those out, your CPU is probably going to be pegged for quite a while, depending on how resource intensive your workload is. So it can be a very, very bad thing to do in a production environment. So I do not recommend that. But for here, for the environment that I'm on, it's just fine. So let's go ahead and run this just to show that there are no plans in cache, and there are not. Okay. So here we're going to look at a series of queries, and we're going to kind of get a feel for what's going on kind of under the covers with these queries. So this first query, I am looking for return all the columns from sales.salesorder_detail where product ID equals 897. Okay, notice that I am using a select star. Okay, I don't recommend using select star just because in most cases you do not need all columns in a particular table to satisfy a query. Okay, here I'm doing it for a specific reason, which it will kind of come to light a little bit later, but looking for all the records in that table where the product ID equals 897. The product ID is a non-clustered index. Okay, let's go ahead and run this. Okay, let me go ahead and run this again, include my actual execution plan. Okay, here we return 2 records, all the columns from that table. Looking at the messages column, we have 10 logical reads. Okay, so 10 pages read from memory to satisfy this query. Looking at the execution plan, we have an index seek, so we're able to find the specific records in that index that we want. But because we're using the select star, okay, we have to go out to disk to get the additional columns that we need to satisfy this query. That's what this this key lookup is, also known as a bookmark lookup. Okay, this is a very resource-intensive operation because it has to happen for every single record that we return. Okay, we can see that the overall cost for this operation is 98%. This is really going to come into play a little bit later when we look at comparing a couple of different queries. Okay, so but for the most part, this is a relatively efficient operation for this query. Here I'm performing a very similar query to the one we had before on the carrier tracking number column. Okay, here I'm looking for a specific value. I'm going to return all the columns from that table for that value. Okay, look at the messages. We have 9 logical reads as compared to 10 before, just because this is a different query. Looking at the execution plan is very, very similar to the one we had before. Okay, so nothing really special there. Okay, but do note that we are using explicit values in our where clause. Okay, here we're using a hard-coded 897. Here we're using a hard-coded string literal. Okay, and this is going to come into play when we start talking about local variables. Okay, here I am declaring a local variable, declaring product ID, and then I'm assigning 897 to that product ID. And then I'm using that product ID local variable as a predicate to our where clause here. Okay, let's go ahead and highlight this query. Return the same 2 records that we had before. Looking at the messages column, now we have 1,240 logical reads. Before we had 10. Okay, 1240 versus 10. So what has happened? Well, let's look at the execution plan first. Here we have a clustered index scan. Before we had an index seek with a bookmark lookup. The only thing that changed here was the fact that I'm using a local variable. Okay? What is happening here is whenever we compile this query, the optimizer does not know what value is in this local variable. Okay? So it has to make some assumptions. Okay? Before it knew exactly what we were passing to it. It knew we were passing an 897, so it's able to tailor a plan based on that 897. Here, whenever it creates the plan, it has no idea what value we're passing to it, so it kind of makes some assumptions. One of the assumptions, and the main assumption that it's making, is the fact that it looks at statistics. Okay, statistics are a histogram that SQL Server keeps for indexes and queries that you are setting where clauses for, where you don't have an index. But it basically is a distribution of data values for that particular column. Okay, SQL Server, since it has statistics on this particular index, it makes some assumptions, and the assumption that it makes is it looks at the average data distribution point. Okay, here it determines, based on the cardinality or the number of unique values in this product ID field, that since there aren't very many product IDs, that it's going to be better served on average to produce an index scan. Okay, producing an index scan here based on the number of unique values, or the number of average unique values in this column. Okay, this is not a intuitive thing at all about SQL Server and just databases in general. You have to have kind of been burnt by this before, or have done research on this to kind of make use of this fact. Okay, here we're doing the same exact thing on carrier tracking number, and I am setting that local variable as a predicate here. Okay, return the same two rows that we had before with all the columns, looking at the messages. And now we have 9 logical reads, which is the same number of logical reads that we had before. So what gives? Looking at the execution plan, the same plan that we had before. Well, again, SQL Server still does not know what value that we're passing to it here. Okay, again, it has to make assumptions. The assumption that it makes is the average data distribution value for the values in carrier tracking number. In this case, since carrier tracking number has a much wider range of unique values, it determines that this query is probably going to be best served on average by running an index seek. Okay? And we can kind of take a look at these data distribution values by just running a simple aggregate query. We can also look at the statistics on this table. Or this index. I'm not going to do it here. You can use DBCC show statistics to look at the indexes, or the statistics for a particular index. But here we're going to basically do the same thing. Okay. Here I'm taking a look at the number of unique values in those columns. Okay. Here we can see that the total number of records in this table is 121,000 and some change. The number of distinct product IDs that we have is 266, whereas the distinct number of carrier tracking numbers we have is just over 3,800. Okay? Based on this information, SQL Server is guessing that our query for the carrier tracking number column here, here, is going to be better served by using an index seek, which is what we saw, and because of the less number of unique values in the product ID column, we saw the index scan before. Okay, this is just some general assumptions that the optimizer is making for us. Okay, one way to get around using local variables is through using parameters. Okay, whenever we use parameters, the optimizer is able to sniff the value that we are sending to that parameter on the very first execution of that procedure. So what does that mean? Whenever we create stored procedures, okay, or just parameterize, or we'll talk about stored procedures. Whenever we create stored procedures, like we are doing right here, this create procedure statement, whenever we create it, it's just a metadata operation. Okay, we're just taking this procedure and we're saving it to the database. Okay, we haven't executed anything yet. On first execution of this stored procedure, a couple of things happen. The first thing that happens is the optimizer takes a look and it sniffs the value that we pass in. Okay, here we'll be passing in the product ID. Okay, and then we're going to use that product ID input parameter as a predicate here. Okay, so this is very, very simple are very, very similar to the statement that we had before when we were using a local variable, but in functionality it's a little bit different because we are passing in a parameter. Okay, so we created this procedure. Okay, I'm going to drop it and recreate it. Here I'm going to clear out our procedure cache. Okay, you can see that there is currently nothing in our procedure cache. Okay. So I'm going to come down here. I'm going to execute this procedure for the first time. Okay, when I execute this procedure, an execution plan will be created and stored in memory for the value 897. Okay, let's run this. Okay, the 2 records that we had are returned, and now we are back to 10 logical reads because the optimizer creates a plan tailored for this 897 value. Okay, look at the execution plan. We have an index seek. Okay, and we still have the key lookup that we had before here. Okay, this is the resource intensive operation that I showed you before, because we have to go out to disk for every single record returned here. Okay, here it's not too bad because we're only returning 2 records. It can get a lot worse when we return more. Okay, so looking at the execution or the procedure cache, we can see that this proc has been called once with a use count of 1. Okay, we see that it's a proc, so that's the only thing that's in our execution cache or our procedure cache right now. Okay. Here I'm going to run that procedure again, but this time I'm going to pass in a product ID of 870. Okay, 870 has a much larger distribution in the sales.sales order detail table than 897 does. Okay, 897 returns 2 records that match up to product ID. 870 returns, I think, around 4,700. So a much wider data distribution for 870. So let's go ahead and run this. Okay, and we return around 4,700 records for the value 870. Looking at the execution plan, we have the same exact execution plan that we had before. Okay, still have the index seek that we had. Remember, this plan that we're using here is absolutely tailored for the 897 value that we first invoke that procedure for. Okay, that plan is going to be reused. Index seek and that bookmark lookup. Okay, still an expensive operation. And notice we're not returning 2 records now, we're returning close to 4,700 records. Okay, looking at the messages column, instead of the 10 records that we have, 10 logical reads that we had before, now we have almost a little over 14,000. Okay, there are only around 1,240 pages in this entire table. Okay, seems very strange that we have close to 14,000 logical reads. Well, the reason for that is the work that has to be done here. Okay, in this index we expect around around 2. Okay, this isn't necessarily going to show that, but we expect around 2 just based on that execution plan that we originally have. And since we're reusing that plan, this I/O operation that we're doing here becomes much more magnified. Okay, so that's why we have the 14,000 and some change logical reads that we have here. So we're reusing that plan, and the reuse of execution plans are 9 times out of 10 a really good thing, just because the creation of an execution plan is a very CPU intensive operation. And for those environments where you have a lot of small queries that are ran over and over again really fast, having to rebuild that execution plan on each call can be a prohibitive operation, just because it could take more time to create the plan itself than it would to run the query. Okay, so 9 times out of 10, reuse of execution plans are a good thing, except in those situations where you have a wide range of data distribution points for input parameters that you could potentially be passing in. Okay, so let's look at our plan cache, and we'll see that that execution plan for that procedure has been used twice. Okay, which is what we expect, because it got we looked at the execution plan and it was totally reused again. Okay, so what happens if we were to free our proc cache and run those in the opposite order? So let's go ahead and clear out our proc cache again. Here I'm going to run the same proc, but this time I'm going to pass in 870 first. Okay, ran 870, returns the 4,700 records that we expect. This time we have 1,240 logical reads. Okay, that's the total number of pages in this table. Looking at the execution plan, we have an index scan. This time it's a clustered index scan, which is essentially a table scan. So we scan every single record in the table, and then based on the touching of those records, we compare that to our predicate, and then we return that value. Okay, so what happens whenever we pass 897 to it? Okay, let's run this query again. return the 2 records that we expect for 897. Okay, 2 records. Looking at the execution plan, we're reusing the execution plan that we created for 870. Okay, remember, on first execution of this stored procedure, we're reusing that execution plan. Okay, we're creating that execution plan, and any subsequent reuse of that plan or any subsequent call to that procedure is going to reuse that plan, so long as there's nothing that has invoked a plan recompile. So here we can see that even though we're returning 2 records, we have to go and scan that index just because that's the plan that's tailored for 870. Looking at the messages, see the logical reads are 1240, even though we're returning those 2 records, which should really incur around 10 logical reads, just because we're having to reuse that plan to satisfy that query. So again, 9 times out of 10, reuse of execution plan is a good thing, but we have looked at a couple places here where it's not. So the ways around that are to have specific store procedures for your really wide varying data distribution points. You could use parameterized SQL. Okay, you can use exec so that a plan is recompiled every time, but using dynamic SQL has its ins and outs there, so it's not always a viable alternative to do this. Also, you can use the with recompile option that's available in, I think, 2005 to make sure that a plan is recompiled every single time for a query. So so that's kind of what I want you to take away from this. Kind of dug into what's kind of going on inside the optimizer from a 10,000-foot view, and then kind of looked at how we can make use of execution plans and how in some situations it doesn't necessarily make sense to reuse those plans. So there's definitely some things you need to kind of keep in mind there whenever you're reusing these plans. Okay. On to cursors. So cursors are a kind of a fun topic just because there's some widely varied camps in terms of the ways of thinking about cursors. Cursors are not inherently bad, right? They can be if they're misused, but they're just a tool. They're a tool for us to use. They're great for when we have to actually touch every single record in a specific table and maybe pass values from those records to store procedures or something like that. So they definitely have their place, but they can be misused just because they're an iterative approach to solving a problem as compared to a set-based approach to solving a problem. And in the database world, using set-based approaches are usually the best way to go about solving a problem, just because that's how databases are tailored. Okay, so here I'm going to kind of look at the syntax of a cursor and a very common way cursors are used, or a common way that I've seen them been used over the years, and how we can look at some of the common aspects of the different part of the cursor and get a feeling for how we can take that cursor, take it out of the iterative approach to solving a problem, and then moving it to a set-based approach to solve a problem much more efficiently. So here, basic syntax for a cursor, we're going to pass it a query that it's going to use as the base. It's going to iterate through each one of these records. Here, it's going to loop through 38 different records. Okay, and for each one of those records, it's going to assign it to a local variable, and it's going to use that local variable to do some stuff. Okay, here for each one of these records, I am looking up in sales.salesorder based on the product ID that I have loaded into a local variable. Then I'm going to get my sales order ID. I'm going to load that into a table variable here. Okay, and then for each iteration, I'm going to go do that lookup, and then at the end, I am going to take this output from this table variable. I am going to join it to my sales.salesorder header table, and then I'm going to do some aggregations based on that data. So let's go ahead and run this. Okay. Returns around a little over 12,000 records. Looking at the messages, we have a lot of I/O occurring here. Okay, because we're using a table variable, we're using a cursor and doing a bunch of lookups each time, and it's not a very efficient operation. Here we can see we have 235 logical reads. Here we have a little over 3,000. Here a little over 2,000. So a very I/O intensive operation just to do it this way. Okay, but if we look at some of the common aspects of what we're doing here, we can kind of get a feel of maybe we could join some of these operations together. So here I'm getting the product ID from production.product where the name's like mountain. Okay, here I'm using this product ID basically as a lookup here to get my sales order ID. Okay, and then we're just putting it into a table variable. Then here, once we've loaded all of our lookups up, we're just joining it back to sales order header and doing some aggregations. Okay, because we're basically doing this lookup here and we're loading some data here and we're doing that lookup down here, we can kind of just take this operation out of a cursor and just kind of do a couple of joins. So here, taking all this logic out of this cursor, performing the lookup on sales.salesorder header and sales order detail based on that sales order ID. Then I'm joining back to production.product where our p.name is like mountain, and then I'm just performing the operation here as a set-based approach rather than an iterative one. So here, run this query. Okay. Here we still have the 12,000 records that we expect, but if we look at the amount of I/O generated, we have 704 logical reads, we have 139, and some change. So it's a much more efficient operation just by taking that functionality out of the cursor-based approach and using it as a set-based approach. A big performance win just by doing that. Okay. Okay. On to temp tables versus table variables. Okay. A couple of things I want to mention about table variables. First is the misconception that table variables are always memory resident only. That's absolutely not true. If we take a look at the number of active temp tables that we have in the system right now based on our sys.dm OS performance counters DMV, we can see that currently on my system there are 0 active temp tables. Okay? In this batch, what I'm going to do is I am going to create a temp table, I'm going to create a table variable. I'm going to load a record into that table variable, and then I am going to look to see if there are any pages allocated in tempdb using sys.dm db task space usage for our given session to see if there's any pages allocated, and then I'm going to see if there are any active temp tables. Okay, so right now there are 0. I'm going to run all of this in one batch. Here we can see that there is a page allocated in tempdb for our given session, and we can see that we do in fact have a temp table here. Okay, since table variables go out of scope as soon as your session or your given batch is done, it should have went out of scope, and sure enough, we look at our counter again, we're back to 0. So there is a presence in tempdb for every table variable, even though it is minimal. Okay. So now we're going to look at basically we're going to kind of compare and contrast using temp tables and table variables, and when it may make sense to use one versus another. Okay. Oh, another thing I want to mention about table variables is that there is a misconception that you can't index them. You can index them, but not through a DDL operation. You have to basically include a constraint in your table definition, and based on that constraint, there will be an index created for you. So here I am. First, I want to clear out anything that's in my proc cache and my data cache. Okay, clear that out. Here I'm creating a table variable. I'm creating a carrier tracking number in it, creating that as the primary key, and then I'm just going to load 1,000 records into that carrier's temp table, or table variable, sorry. And then I am going to join my carrier's table variable to sales.salesorder detail, and I'm going to return some records. So here, let's go ahead and run this. Okay. Returns 48 records. Looking at the I/O, we have, oh, actually I want to include the actual execution plan. It's important here. Okay. Return the 48 records. I want to look at the I/O, and notice that the I/O is somewhat high. We have around 51,000 and some change logical reads, 90 for the sales order detail and additional lookup, and around 7 or so for our table variable itself. Looking at the execution plan, okay, there's not necessarily anything out of the ordinary with this execution plan, except for one thing. Okay, we're doing an index scan on our table variable, and then we're joining that index scan to through a nested loops join to look up on an index on sales order detail. Then we have to go back out to disk to get some additional columns. But the thing I want you to notice here is our scan on our carrier's table variable here. Okay. The one thing I want you to notice is whenever you hover over this line, that the actual number of rows returned is 1,000, which is what we expect because we loaded 1,000 records into that table. However, the estimated number of rows, or the number of rows that SQL Server thinks are in this table variable, is 1. Well, why is that? The reason for that is that SQL Server does not maintain statistics on table variables, and statistics are one of the main things that the optimizer uses when it goes to create an execution plan. Okay, had it known that there are actually 1,000 records in this table, it may have chosen a different physical join. Okay, here it thinks that there's 1, and it's really an ideal situation for a nested loop. But because there are actually 1,000, it turns out it may not have been the best choice. Okay, so SQL Server does not maintain statistics, so it doesn't know how many records are in this table. So that's why it becomes somewhat of a challenge to join table variables to other tables, just because of that aspect of table variables. So if we go and use a temp table instead, statistics are maintained on temp tables. I'm going to create our temp table with the same structure that we had before, and then I'm going to load 1,000 records into it. Okay. Now I'm going to perform the same join that we had before. Instead, I'm using a temp table instead of a table variable. Okay. Look at the number of rows, 48 records returned, which is what we expect. Look at the amount of I/O. We have 709 logical reads as compared to the 51,000 logical reads that we had before. Looking at the execution plan, and it's a different plan. Okay. We still have the nested loop, but this time we have the nested loop based on the index lookup. Okay, in this case we have 228 actual records returned, and it estimated that 228 records would be returned. So it's an accurate representation of what it wants. So it joins those records together based on that bookmark lookup, orders that particular result set. Okay, order it. You see the join here, so we have to order it because we are using a merge join. Okay, so a merge join looks at 2 ordered sets, merges them together, and then once the smaller number of the sets is completed, then it knows that it is done. So it's a very, very efficient operation for those data sets that are already ordered. So here we didn't, in the first query, we didn't have a merge join. Here we do have a merge join. It turns out it is a much better operation for what we are attempting. Looking at the actual versus the estimated number of rows here from our temp table, and they match up exactly. Okay, we have actual 1,000 and estimated 1,000, whereas before we had an actual number of 1,000 with the table variable with an estimated of 1. So the more insight that the optimizer has in terms of the number of records that are being returned from any point of a given query, the better off you are going to be, because it's going to be able to choose a better plan in most cases. Okay, so that's just kind of some insight into when you may want to use table variables versus temp tables. Now, I'm not suggesting that you never use table variables, because table variables can be a very, very valuable tool. And even in some cases, when you use with recompile, you can actually get an insight into the amount of records that are in those tables. But really more of a challenge whenever you have to join table variables to other tables. But if you're just loading data into table variables and using that for display purposes, they can be a very, very, very good tool for that. Okay. On to user-defined functions. Okay. In SQL Server, there are 3 types of user-defined functions. There is a scalar-valued function. Okay, I'm going to omit any sort of CLR functions here. I'm just going to talk about TSQL functions. There is a scalar-valued function which returns 1 record. Okay, 1 value. There is 2 different types of table-valued functions. Okay, there is a multi-statement table-value function, and there is an inline table-value function. We're going to look at all 3 of those today and get a feel for when we may want to use one versus another. So here I'm creating a scalar function. Okay, it takes sales order ID. Okay, does a lookup on sales order ID, assigns that to a local variable. Okay, then it's going to return that local variable. Notice that I'm using begin and end here. Okay, so I'm going to go ahead and create this local variable. This table valued function. I'm sorry. I'm going to go ahead and create this scalar UDF. Okay. I'm going to right click and include actual execution plan. Okay. And here I want to, because whenever we use functions, SQL Server or Management Studio is sometimes not very honest with us in terms of what's going on. So I'm going to go to Tools, SQL Profiler, just because I want to see what's actually occurring on the system rather than having to rely on a couple of different things here. So I'm going to run Profiler, maybe. Connect. Okay, I'm going to have a template for this. Okay, I'm going to go ahead and run this. All right. So I'm going to invoke our scalar UDF that we just created. So I'm going to do it in the select clause because it is a scalar UDF, and I'm just passing in the sales order ID to this UDF here, and then I'm going to look at the amount of I/O for a particular product ID. So let's go ahead and run this. Okay. This returns around 3,007 records. Looking at the I/O involved, there are 9 logical reads. So 9 logical reads to return a little over 3,000 records. It seems maybe a little bit fishy. Look at the execution plan. We can see that we have an index seek. Well, that kind of makes sense because we are performing a operation against an indexed field. So I mean that kind of makes sense. But the strange thing is that we go back to our messages column. We're only seeing I/O for sales order detail, okay, which is what we're using in our from clause here. But that function actually goes out and hits sales order header. Okay, so I'm really not seeing much in terms of what's going on against sales order header. If we go out to profiler, we can see that in actuality the number of reads that we had on this table was really a little more than 50,000 as compared to the 9 that we see in the I/O in Management Studio. That's because that function call occurs against every single record. Okay, we don't really see that in Management Studio whenever we look at it that way. Okay. So that's something to kind of look out for. So whenever you use a scalar function in a select statement or where clause or whatever, it may look really, really good in terms of I/O returned. Even at the execution plan level, it looks pretty good. However, if you turn to profile, you get a really, really more accurate representation of what's going on under the hood for that function. So one thing I can do is and we can see that using this function call returns a very, very inefficient way to go and gather this data, right? Just because we have to invoke this function on every single record. Well, one way to kind of get around this is to use something known as an inline table value function. Okay, you can think of an inline table value function as almost like a parameterized view. Okay, it takes a input parameter. Okay, and then it doesn't use begin or end. We tell SQL Server that it's going to return a table, and then we basically form a select statement inside the return clause. Okay, you can't do any sort of temp tables or anything like that in here. We just have an inline statement that we return with. So here I'm taking that sales order ID, using that as a predicate here, and then that's going to be what I return. Okay, so let's go ahead and create this. Okay, come down here, and now I have to use cross apply because I am going to be passing in sales order ID from the sales order detail table, and the only way to pass that value in is through a cross apply operator. So I'm going to do that, and I'm still setting the same criteria on for product ID 708. Let's go ahead and run this. Okay, same 3,007 records returned. Looking at the I/O involved, and we see that we have around 70 or so logical I/Os. Okay, looking at profiler, we can see that that actually matches up pretty well. We have 84 here, so we have a little bit of a discrepancy, but that's something I can live with because it is a lot better than the 50,000 or so that we had up here. So 84 in my book is much better than the 50,000. Okay, looking at the execution plan, and sure enough here we have a more accurate representation. So here we have an iterator, an index seek that's hitting sales order detail. We have an index scan that's hitting sales order header. There's probably some tuning that we can do there, but using this inline table value function is a much more efficient way to return the same value that we had before, just doing it in line. Okay. The other type of table value function is a multi-statement table value function. With a multi-statement, we pass in an input parameter. Okay, then we define the table variable that is going to be returned. Here, declaring a table variable. This is going to be the output of the table variable, and then basically using begin and end. Okay, notice that we're using begin and end, and then we are basically doing that lookup here on that sales order ID, inserting it into our table variable, and then we're going to return that. We don't have to pass anything to a return operator. So here, let's go ahead and create this. Okay. I'm going to perform the exact same operation that we had before. using the cross apply, and except this time our function is a multi-statement function as compared to an inline function. So let's go ahead and run this. Okay, returns around 3007 records, which is what we expect. Looking at the I/O involved, I have 3007 here, 9 logical reads. I'm somewhat inclined to believe this. Looking at the execution plan, we have an index seek on our sales order detail table, and then we have this iterator, which is a call to a table valued function. Okay, this makes me suspicious. Okay, good thing I had profiler running. So go over to profiler, we can see that actually this function call resulted in around 83,000 logical IOs. Okay, which is significantly more than the 84 logical IOs that I had before with my inline table valued function. So you can see here that in most cases, especially for what we're looking at here, whenever we return a small result set, using an inline table value function can drastically outperform a scalar function and a multi-statement table value function. Okay. All right, on to our last example, correlated subqueries. A correlated subquery is basically, you can kind of think of it as a loop inside the database engine. Okay. Here I'm returning everything from sales.salesOrder header, okay, and then I am, based on what's returned from sales order header, doing a lookup on sales order detail, okay. Then I'm doing a lookup again on sales order detail based on the sales order ID. So each sales order ID from this table, I'm doing a lookup, and then I'm returning an aggregate for quantity and unit price from sales order detail, okay. Right click and go to include actual execution plan. Let's run this. Okay. Return around 31,000 records. Looking at the I/O involved, we have, I don't know, around 3,100 or so logical IOs. Looking at the execution plan, kind of a more complicated execution plan, so I'm not going to kind of dig into it very much, but we have some things that we would kind of expect based on the query that we're doing. We have some joins, we have a couple of scans, so not necessarily a bad index plan, but a different kind. Okay. So one way we can kind of rewrite this, remember we had around 3,100 or so logical IOs for this query. Coming down here, and I can use the cross apply to kind of do that same lookup as we had before based on the sales order ID and perform that aggregate. Okay, so let's go and run this. Return the same 31,000 or so records. Looking at the I/O, and wow, look at the I/O. 101,000 and some change logical IOs just by using this cross apply. Okay, so what really is going on here? Well, using this cross apply and passing in this criteria, we can see that we're actually, for each single record, we're kind of going out and doing this aggregation, and then we're going to kind of settle up at the end for all that data. So it's a very inefficient way to do this. Okay, so well, maybe there's a better way. So let's come down and let's actually create a inline table value function, because we saw in the last example that inline table value functions are usually a good thing, right? So here I'm going to create our function. Okay, I'm going to pass in that sales order ID. I'm going to kind of go do my aggregates here, and then we'll go from there. So let's go and notice we're still using the cross apply. Okay, passing in that sales order ID, and then we're doing our aggregates that way. Let's go and run this. Okay, return around the same 31,000 records that we expect. Looking at the I/O, and not made any improvement on that. Okay, have not made any improvement at all, just because of the work that we have to do inside of that cross apply operator. Okay, well, really what we kind of want to do is eventually turn this into a join, right? Well, one way to do this is to kind of make it so this query is no longer correlated. Okay, here I am taking this aggregation and I'm kind of segmenting it out. So I'm doing it for every single record. Okay, for every single record in sales.salesOrder detail, I'm aggregating the unit price and I'm aggregating the quantity. Once I've done that aggregation, I am joining that result set from this derived table back to sales order header, and I'm returning the records that I want. So here, let's return this. Okay, return the same 31,000 records that we saw before, and now we're back to around 3,100 or so logical reads, actually less than that. or around 2,000 or so logical reads for that same query. Okay, it's because we are actually able to kind of abstract that aggregation, do it once, and then join that result set back to sales order header. Well, really what we kind of want to do is just do a join and return the aggregation itself. So here I'm kind of taking that subquery totally out of the mix, okay, taking that out, abstracted it, so then I'm just doing a join between the sales order header and the sales order detail tables, and then I'm doing the aggregations that way. So here, let's go ahead and run this. Same result set returned, looking at the messages, and we're right around where we were before in terms of logical reads. So we're around 1,900 or so logical reads. Well, that's strange. I mean, this statement looks a lot different than this statement, right? Well, not really, because these are really essentially the same patterns, okay? SQL Server is smart enough to know that at the end of the day, this query here with its join and its subquery is exactly the same as what we're doing here. Because they're the same pattern, they're going to end up with the same plan, okay? So if I run these two statements together, okay, same result set for each. Looking at the I/O matches up exactly the same, okay? Looking at the execution plans for these two, execution plans looking at the amount of relative cost for each one, 50%, and the plans actually ended up being the same plan. So these two queries, while they are written differently, end up being the same pattern, so they end up having the same performance. So there are cases where you can use correlated subqueries efficiently, but whenever you're using aggregates, kind of be wary of using cross-apply and that type of functionality with them. So that pretty much concludes what I wanted to talk about today in our Writing Faster SQL Server Queries introductory session. I plan to have a more in-depth or a more low-level session a little bit earlier in 2011. But I hope you enjoyed today's session. I enjoyed performing it, so I look forward to seeing you at future Experts Exchange webinars, and I hope you had fun. Happy holidays, and I'll see you later.
Thank you, Tim. I think that it's safe to say that we all learned a lot of really valuable information here. As I said earlier, you can get in touch with me if you would like to know more about Experts Exchange, or if you would like to talk with Tim about his consulting work for SQL Server and other things. You can contact him at this email address that you see here. Thank you all for attending Writing Faster SQL Server Queries Part 1, and keep checking your email inboxes as well as YouTube for Part 2 of Writing Faster SQL Server Queries. Thanks again.